Hello and good morning. In this presentation, I will discuss some ideas on synergizing EOR projects with CO2 storage to reduce our carbon footprint and achieve our goals of having a sustainable net zero emission system. As you may remember, we have had cycles of increasing and decreasing interest in carbon capture, utilization, and storage projects. But my hope is that current surge of interest in CCUS projects is sustained and we will see more and more larger-scale CCUS projects in the near future. Here is the outline of the presentation. I will have a quick look at the motivations to do more CCUS projects, followed by a few definitions related to carbon life cycle analysis for carbon neutrality assessment. Then I will use an example from Cranfield and follow that with some ideas on how we can synergize EOR with the storage projects. I will finish the presentation with final points and some conclusions. Considering current environment in oil and gas industry, there are two main driving forces behind a possible surge in CCUS projects in the future. First, CCUS becoming an integral part of oil and gas companies' ambitions to achieve net zero emissions by 2050. In addition, 45Q tax credits and other incentives for captured CO2 has made CCUS more attractive. And now when you do the numbers and consider all the factors involved to deploy a CCUS project, you can make a case for an acceptable investment. I have taken this figure from National Petroleum Council's report in 2019 that estimates the required tax credit per ton of CO2 to incentivize the capture of stationary sources of CO2. With current levels of credit at $50 per ton, there are around 25 million tons of CO2 per year that can be captured. And to reach 500 million tons captured per year, tax credit has to gradually increase to around $110. This tax credit has started a wave of interest in companies to take a serious look at CCUS. In the next few slides, I will provide an example from a CO2 EOR project, and I will quickly review the process of estimating carbon emissions for a CO2 EOR project. But before that, I would like to refresh your minds with a few definitions which are critical to our discussion. In order to estimate carbon neutrality, you have to define a boundary around your system, where you can assess the carbon input and output of the system and calculate the overall balance. This would allow us to decide if we are running a carbon neutral or net zero emission operation or not. There are three boundary definitions when it comes to the carbon life cycle analysis. First definition is called cradle to grave, that encompasses all the elements of carbon life cycle analysis shown here in a red box. Another definition is called gate to gate, that draws the boundary only around the EOR operation, ignoring the subsequent emissions of the produced oil. This is shown here by the black box. And finally, gate to grave, where only elements downstream of CO2 EOR operations are included into the carbon life cycle analysis. This is shown here by the blue box. In next few slides, I will introduce a CO2 EOR site, and we will take a look at the amount of CO2 stored versus total emissions when gate to grave and cradle to grave system boundary is considered. As an example, I have selected Cranfield site because of our center's involvement in CCARB's monitoring program. We use numerical simulations to history match the CO2 EOR operation and extend the results over time and develop other scenarios. We use outputs of these models to estimate the CO2 storage and oil production amount to use in our storage versus emission calculations. In all scenarios, we have considered 25 years of injection, either with continuous gas injection, CGI, or water alternating gas or VAC injection. Also, we have added water curtain wells to CGI and VAC to create two hybrid scenarios. In next slide, you will see the results for the carbon balance for these four different scenarios. Here, for the sake of the time, I will jump to the final results of the study without too much discussion on details. To help visualize the emission and storage relationship, we plotted the evolution of the carbon balance of the gate to grave CCUS system over time. Different colors here representing different gas separation processes. There is also a no separation case shown in black. In these figures, the y-axis is showing the carbon balance. A negative carbon balance associated with the CCUS boundary means that more CO2 is being stored than is being emitted at that point in time. It also means that for as long as the carbon balance is negative, the oil produced is net carbon negative, and the CCUS system operates with a negative carbon footprint. The main takeaway is that all four scenarios start operating with a negative carbon footprint and at some point transition into operating with a positive carbon footprint. VAC is showing the best performance in being carbon neutral. This shows how operational strategies can impact the carbon neutrality of the project. Here, we expand the results to cradle-to-grave system boundary, which includes upstream emissions. Capture assumed to be from a coal power plant, and as you can see in these graphs, the impact of the expansion of the system to account for the upstream emission adds to the overall emissions of the system, making it even harder to achieve carbon neutrality. Clearly, we need to store more CO2 to achieve carbon neutrality over the time of this project, and this is where the saline storage can help. What we have seen so far is showing how by managing our operations within the CO2 IOR field, you can manipulate the transition point from net carbon negative to net carbon positive operation. This is by selecting to do CGI, VAC, maybe trying different VAC ratios, etc. In all these scenarios, the stored amount of CO2 is simply calculated based on this equation, where we deduct the CO2 losses from the amount of the purchased CO2 measured at the entry of the field. Standard schemes that we have discussed so far, including using CGI or VAC or other combinations, are limited in terms of total CO2 storage capacity. And in case where you need to divert larger amounts of CO2 for storage, you may not have enough capacity. This is where you can think of expanding the surface volume defined by MVA program, shown here in green box, to include stacked storage and fetch and trap. This would allow us to store larger volumes of CO2 and deal with economic uncertainties around our project. Stacked storage and fetch and trap can be done either on a standalone basis, or it can be attached to an IOR operation. I will try to elaborate on these ideas in the next few slides by showing some general scenarios. First, let's take a look at the idea of a stacked storage. Here at the top, you see a cross-section from Texas Gulf Coast going from onshore on the left to the offshore on the right. This geology offers us thousands of feet of porous media, which historically has been used for oil and gas production, and you can potentially use them for carbon storage. At the bottom cross-section, we have removed the overpressure zone and zones where CO2 will not stay in supercritical phase to get a picture of the potential pressure window that we can target for CO2 injection. After this preliminary assessment, you can zoom into the areas of your interest and have a closer look at the possibilities for stacked storage near your intended project. Here, we are zooming into the Southwest Louisiana, where historically lots of oil and gas production has happened, and there could be potentially many sites for CO2 EOR and storage projects. In this case, I'm showing how you can target an EOR operation in Frio formation below the Anahuac Shale, and at the same time target some of the overlaying sand shelf sequences in Miocene age formations for stacked storage. In this scenario, we have expanded our subsurface volume vertically to increase our MVA-defined volume, again shown here in green box. This way, at the location of EOR site, we have access to larger pore volumes for CO2 storage to be used on an ad hoc basis along our EOR operation to meet our financial and carbon neutrality goals. Obviously, this will not be without any issues or problems, and there will be challenges that will require us to do some more work. For example, a few things that immediately comes to mind includes the lack of information, including injection and production data, lack of core samples, or geophysical information. Also, next question would be how we can trust these formations to keep the injected CO2 where we may lack a traditional seal. Are these zones charged with hydrocarbon and leaked, or they have never been charged with hydrocarbons? This is where more research is needed to better understand the impact of the non-traditional sand-seal pairs and impact of local heterogeneity on the capability of these formations to store CO2. Now, let's take a look at the Schleifner project, where you can see some similarities with the idea of static storage. In the Schleifner project, CO2 has been successfully being injected for many years. As you can see, CO2 has been migrating from pool to pool under many small barriers, and its trapping has been proven by extensive seismic imaging. This example looks very similar to many sand shale sequences that we see in geological formations in North America. In Schleifner, over 17 million tons of CO2 has been injected in about 200-meter thick sand, where in Gulf of Mexico, we have access to over 1,000 meters of sand and shale sequences that can be used for CO2 storage. This is where we have to improve our understanding of these systems and engineer our way to use these resources. Another natural extension to this static storage idea is to expand or refine MVA volume horizontally and inject the CO2 way down deep in the fetch area. This would allow us to fetch the CO2 down deep of the target formation and trap it later in targeted area, either for storage or IOR. This can help to maintain the pressure up deep in IOR patterns while benefiting from storing larger volumes of CO2. Many types of designs can be envisioned here to time the arrival of the CO2 to the trap area to either use it for CO2 storage or for IOR. Here you can see the fetch and trap idea in a closer look. In this setting, enhancing the trapping in the fetch area is important, where we will try to maximize the dissolution and capillary trapping in fetch area, and again, improving our understanding of interaction between buoyancy and capillary forces in heterogeneous formations becomes critical. You can also envision a combination of this method with a stack storage, and there will be signs that these ideas may not be best suited for them. Similar to static storage, we will have some challenges for fetch and trap systems. Again, lack of information down deep of the trap could be an issue, where not as many wells being drilled. Also, finding the best location to fetch the CO2 is important to make sure CO2 travels in intended paths, so we have to characterize a larger area. To wrap up my discussions, I decided to do some rough calculations and share some numbers with you with the hope that it may ignite an idea or create some discussion points. Let's do a crude comparison of saltwater disposal and CO2 storage. A commercial saltwater disposal operator will typically charge between $0.50 to $2.50 per barrel of saltwater. This price variation is mostly because of the supply and demand, and for example, in Texas, we are closer to lower bound of these values. Also note that I have not included any capture or transportation costs here. Next, I took the tax credits of $35 per ton in EOR case and $50 per ton in a storage case, and did some unit conversions and assumed a typical geological formation fees for CO2 injection. This would give you about $4.6 per barrel of stored CO2 in EOR case and $6.6 per barrel of stored CO2 in a storage case. This is about 2 to 10 times more than saltwater disposal per barrel of disposed fluid. Next, if you take the average of $4.6 and $6.6 from previous slide at $5.6 per barrel of stored CO2, assuming you are running a combination of CO2 EOR and storage, you can come up with a quick way to back calculate the amount of storage that you need to attach to your EOR operation that would make sense to your financial and carbon neutrality goals. You can run CO2 operations with different net utilization ratios, where you distribute your CO2 between EOR and storage. Net utilization ratio defined as amount of purchased CO2 to produce 1 barrel of oil. This table gives you a rough idea on how much extra you're actually making on top of each barrel of oil by running your operation with different net utilization ratios. For example, you may run your operation with net utilization ratio of 10. That would make you an extra of $3.2 per barrel of oil, which is an 8% increase, considering a $40 base price for oil. Or you may decide to do more storage and increase your overall net utilization ratio to 50 and add an extra of $16.2 per barrel of oil. Obviously, the best net utilization ratio should be optimized here based on the predefined goals of the project. My final points are that we can manage the CO2 operations in different ways by actively balancing IOR and storage elements to achieve carbon neutrality and run a more resilient project. We need to re-examine our economic models based on these new variables to be able to fully benefit from current incentives to do more CCUS projects. Also, we need to start to think, plan, operate, and optimize our business under these new constraints. For example, you may want to consider some of these ideas when you're looking for your next CO2 EOR field, and ask yourself, does this field have access to stack storage? How much do we know about the fetch area of this field? Down the road, to some extent, these considerations can mitigate the risk of unfavorable EOR results and uncertainties in oil prices by providing you with more options to run your operations. To deploy these ideas in larger scale, there are some challenges, and I mentioned a few of them, but we can build on decades of experience in oil and gas industry and retrain our workforce to perform under these new constraints, and hopefully to do more CCUS projects in the future. At the end, I would like to thank our sponsors at Gulf Coast Carbon Center for their support, and would be more than happy to answer any questions when Q&A session opens up. Thank you.